Hello everyone, this is Balasubramanian, working as an Associate Professor in the Department of Computer Science and Engineering at Engineering College. My overall teaching experience is 20 years and I have been associated with Engineering College for the past 16 years. And I would like to record my GATE lecture video on my favorite paper, databases. So this is what GATE 2025 syllabus for database is. We start with ER model and then comes relational model and we have relational algebra. So this is what my today's topic, relational algebra, and we have tuple calculus. So to know tuple calculus, you have to know about relational algebra is, and to know relational algebra, you have to know about relational model, and to know relational model, you have to know about ER model. So this is how the syllabi is framed actually. Then comes SQL. Yes, integrity constraints is coming in SQL, and we have normal forms. So all types of normal forms being covered here. So it is given in a single keyword normal forms, but we have first normal form, second normal form, third normal form, BCNF, fourth normal form, and fifth normal form. Then we have file organization followed by indexing, which comes under file organization, and then we have transactions and concurrency control. So it's a syllabus of databases. It is coming under section 9 of GATE 2025 syllabus. So my today's topic will be on relational algebra. Yes. To start with, before getting into relational algebra, you have to know about how our queries are being processed. So what is a query actually? Yes. So we, you know very well that all our data are stored in the database and we retrieve all data in the form of query. Example for databases, we have Oracle database, we have Microsoft SQL Server, we have IBM DB2. Yes, these are the popular traditional structured databases available across the globe. And so the universal language which is used to interact with the database is SQL, which stands for Structured Query Language. So if you want to interact with the database, we have to develop a SQL query to talk to the database. So all of the SQL queries, right, are being processed finally into machine level language, and this is what the steps involved in processing a SQL query. So what actually we know, being an end user, I just give a query and the database is returning me the data. Yes, for example, I have a table called student. I just want to retrieve all information about all students from the table student. So what is the SQL query which I give to the system is, I'll be giving select star from table name student. That's it, right? So in spite of that, I'll be getting the output. I'll be getting all data from the student table. So SQL query is finally converted into, it is giving me the output, right? I give a query, I get the output. So these are the steps behind the query processing, what is actually happening. So whatever SQL query we give is converted into relational algebra expression, and this is what my today's topic is all about. Yes, and this relational algebra expression is then converted into execution plan, and your execution plan is then converted into your query output. So this is what my query all about, which means that select star from student. So this query is actually converted into relational algebra expression with the help of parser and translator. And relational algebra expression is converted into execution plan by optimizer, and your execution plan is converted into query output by evaluation engine. So these are the basic steps involved in query processing, which are parser and translator, optimization, and evaluation. All the three steps are being identified by diamond symbol. Yes. As I said earlier, these are the basic steps involved in query processing, parsing, translation. So what parser actually does? Parser checks for syntax and verifies the relation, whether the syntax is error-free or not, and whether this relation exists or not. So this is what the functionality of parser actually. If the given SQL query is error-free and it is really a valid table, the parser then handovers the query to a translator, and translator converts the query into relational algebra expression. And next is the relational algebra expression is given as an input to the optimizer, and optimizer is developed developing a query evaluation plan, and the query evaluation plan is given as an input to the query evaluation engine, and it is giving the output by retrieving the data from the database. This is what the steps involved in query processing. This is required to know more about relational algebra. Yes. So my today's GATE lecture video is on relational algebra. Yes. These are the 6 basic operators associated with relational algebra. The first operator is select, denoted by sigma. The second operator is project, denoted by pi. And the third one is union, and fourth one is the difference, Cartesian product, and rename. So union, set difference, Cartesian product are very popular operators which we have already learned in our normal algebra. Yes. So what is actually relational algebra? It is a procedural language, yes, consisting of a set of operations involving all these operators that takes one or two relations as input and produce a new relation as a result. So this is what a relational algebra expression all about. And we all have already said you earlier, your SQL query is converted into relational algebra by parser and translator. So that is why we are here, we are learning relational algebra in detail. And your relational algebra is converted into machine level language by your optimizer and your query evaluation engine. That is the final output. Yes. So the first operator is actually select operator, which is denoted by sigma, which is going to learn each and every relational algebra operator more in detail in the upcoming slides. To start with, the first relational algebra operator is select operator. We call it as a select operation, which involves select operator. So what is actually called a select operator? Yes, if I want to retrieve data from a database based on a condition, yes, I have to go for a select operator. That's very clear. For example, yes, come on now. I have an example over here. I have taken an instructor relation which has 4 attributes: employee ID, employee name, department name, and salary. My question is, come on, select all tuples of the instructor relation where the instructor is in the physics department. Yes, so which means I'm asking the database to give me all instructors who belongs to physics department. So that is my query. Yes, so the condition is the instructor should belong to the department physics. So that is what the condition. So we call it as a predicate. So my predicate is department name is equal to physics. Yes. So its equivalent SQL query is actually, let me write the SQL statement for the given question. Yes. It is actually, here we have the relational algebra expression. So let me first write the SQL query which is known to all, right? So my question is, selecting all tuples of the instructor relation where the instructor belongs to physics department. Come on. So the statement which I have to go for is select statement. Yes. So it is select all data. I require all the 4 attributes, right? So select star from instructor, that the table name, and condition. You know, we have to apply condition using var class in SQL. So these are basics, right? Var department name is equal to physics is equal to physics. Since physics is a non-numeric data, it has to be enclosed within double quotes, right? And data are always case sensitive as far as database is concerned. So this is what the SQL statement for the given question. Select star from instructor is, I think I've given you instruction here. So better instructor, that department name is equal to physics, right? And the equivalent relational algebra expression is this, right? Since we have a condition in the select statement, the right operator to use for is select operator. Is because if you are, as I said earlier, if you are retrieving data from database based on a condition, we have to go for select operation, that is select operator. Yes. So the notation is sigma, and this is the predicate, is the selection. This is what the condition is all about, and R, right? So sigma, and you have to give the predicate condition over here. Department name is equal to physics, and the relation is actually instructor. So this is the equivalent relational algebra expression for the above sequence statement. Yes, and this is what your output is. There are two instructors, Einstein and Gold, who are working in physics department. Yes, and so we'll move to the next slide. Yes. So what are all the operators that can be used in the select predicate? As of now, in the previous slide, I have used equal to, right? Department name is equal to physics. So I can use not equal to, greater than equal to, less than equal to in the selection predicate. Yes. And similarly, you can combine, there might be situations where you have to combine two or more predicates together. Yes, it is possible. You can have two or more conditions in a relational algebra expression using some connectives. So these are the connectives used and, or, and not. Right? And I have another question here. Come on. Find the instructors in physics with a salary greater than $90,000. So here we have two conditions. So if you have two conditions, you have to use connectives, either and or not, right? So the same query is, the previous query was talking about the instructors belong to physics department. Now we have asked for the salary details, right? So the condition is department name is equal to physics and salary greater than 90,000, and the relation remains the same. And since we are involving predicates, that is condition, the operator used is actually sigma, select operator. Yes, fine. The second operation of the second relational algebra operation to be deal with is project operator. Yes. So what is actually called as project operation? Project operation is a unary operation, which means that it involves one relation. Operations involving one relation is actually called as unary operation. You select project operations or unary operations. Yes, so that returns its argument relation with certain attributes left out. Imagine that instructor table has 4 attributes. You don't want all the 4 attributes. You have to leave out few attributes. You just want only 3 or 2 columns. You have to go for project operation, right? And the project operator is actually denoted by pi, and this is what the notation is. Pi, A1, A2, A3 up to AK are the attributes, and small r is the relation. Yes? And the result is defined as the relation of k columns obtained by erasing the columns that are not listed. If I want to left out few columns, I have to go for project operation. Yes, and the resultant of project operation will have only unique rows. Duplicate rows will be removed from the result since relations are sets. And this is what an example for project operation. So for every relational algebra operation, we are looking for an example, right? So here my question is, after we have taken the same instructor table with the same number of attributes, my question is, eliminate the department name attribute of department name attribute of instructor table. So instructor table has got 4 columns. You know that ID, name, department name, and salary. I just don't want the department name alone. Remaining columns I just require it. Okay, so I just want only 3 columns out of 4. So the preferable operator is actually project operator. So here, you know the syntax in the previous slide. It is pi, specify the attributes which you require. Okay, so here you have pi followed by except department name. I just want remaining all attributes. So ID, comma, name, comma, salary from the relation instructor, and this is what your result is. So out of 4 columns, I get 3 columns. So the preferable operator is actually project operator denoted by pi. The third operator is actually union operator. So union operator is not a unary operator because it is not going to involve one relation. It is going to work on minimum 2. Yes, it is going to work on 2 relations. So union operations allows us to combine 2 relations, and the notation is R union S. R is a relation, S is a relation. So it has got some instructions to be followed up. It has got a protocol. Yes, so union operation, intersection operation, set difference operation, Cartesian product. So remaining all operations involves 2 relations which has got some instructions to be validated. The first instruction is relations R, S must have same arity. Yes? It's very important because I'll not repeat the instructions for other operations. It is going to be same for instruction, intersection and set difference, Cartesian product also. So R and S must have same arity. What will be arity? It means same number of columns, same number of attributes. So you can involving two relations should have same arity. Arity means same number of attributes. For example, if relation R has 3 columns, relation S also should have 3 columns. And second point, the attribute domains must be compatible. For example, the second column of relation S deals with the same type of values as the second column of S. For example, if the second column of relation R is talks about instructor name, then the second column of relation S should also be instructor name. That is what actually called as compatible. Yes, the first thing is two relations must have same arity and it should be compatible. And the example what we have taken here is to find all courses. Come on, I have taken a different relation. It is section table. So we have 4 columns here: course ID, section ID, semester and year. So which course has been taught in which semester, which year. So this is what the table is all about. Now my question is, find all courses that were taught in the fall 2017 semester or in the spring 2018 semester or in both. So this is what my question, right? So this relation involves, this question involves two relations. My first question is, I just want to retrieve all courses that were taught in the fall 2017 semester or in the spring 2018 semesters, right? So the query is so I have to retrieve data first. My first condition is actually, come on, list out all the courses that were taught in the fall 2000 semester, right? So we have a column called semester and we have a column called year, right? So since I'm going to retrieve data based on a condition, the operator which I'm going to use is actually sigma, right? Sigma, and the semester is actually fall and the year is actually 2017. You can use the connectives because you can use the and connectives. I just want the courses that were taught in fall semester in the year 2017. So semester is equal to fall and year is equal to 2017 is or spring 2018 semester, right? So sigma, semester is equal to spring and year is equal to 2018. So if you want to find out all the courses that were taught either in fall 2017 semester or in spring 2018 semester, the right operator to be used is actually union. Yes, if you want to know the common courses that were taught in both fall 2017 semester and in spring 2018 semester, you have to go for intersection operator. Yes, so the remaining things remains the same for intersection operator. Let me have a quick glance. Yes, so this is what the result is. These are the courses that were taught either in fall or in spring or both. Okay, yes. Quickly move on to intersection operation. Yes, so definition is, intersection operations allows us to find tuples that are in both the input relation. So common data or intersection relations always retrieve the common data. Yes, common to both the relations. Notation is R intersection S and the instructions remain the same. R and S should have the same arity and it should be compatible, right? And the same example has been taken here also. Come on, list out the courses taught in both fall 2017 and spring 2018 semesters, and the only thing is I just want the common courses that were taught in both the semesters. The only thing is instead of union you have your intersection because you have to retrieve the common courses. The only common course is CS 101 which is taught in both the semesters, right? And set difference notation is going to be, right, R differences S, and the instructions are going to be same. R and S should have same arity and the attribute domains of R and S must be compatible, and we are using the same example, right, with a slight modification. Find out all the courses taught in 2017 fall semester but not in 2018 semester. List out all the courses that were taught in 2017 and which was not in 2018 semester. So the query is, yes, And since this query involves two predicates, I'm just going to use your select operator S. So semester is equal to fall and year is equal to 2017 S, and difference semester is equal to spring and year is equal to 2018 S. So it retrieves courses that were taught in the fall 2017 semester and not in the 2018 semester. So this is what already we have learned in our mathematical algebra. It is A difference B, right? And so these are the two courses that were taught in the fall 2017 semester and not in spring 2018 semester. So my first question is, what does RET mean? So this question has been taken from the previous Sol GATE exam question papers. So what does RET mean? It's very simple, right? As I said, RET means it is same number of attributes. So number of entries in the table? No. Number of samples in the table? No. Number of attributes in the table? Yes. So right. So operations that involves two relations, which means your union, intersection, set difference, Cartesian product has got this word RET. So RET means it is same number of attributes, and the answer is C. RET refers to the number of columns in a table. Yes, number of columns in a table. For example, they have given a relation. If a relation has got 6 attributes A, B, C, D, E, F, then the RET is 6. So RET means number of attributes in the table. That is what called as RET, right? And we have a separate keyword called compactable. The attribute domains of the attribute domains of the value should be same. Yes. And the next question is, I have a SQL query here, right? Total number of tuples returned by the below query. The question is, select star from student table where age greater than 65 and gender is equal to F. Yes. So this is what my student table all about. I just want to retrieve all students whose age is greater than 65 and gender is equal to F. So we have 2 female students with age 70 and 85, and my constraint is age should be greater than 65. Yes. So the example, sorry, I didn't notice the last student. So we have 3 female students with age 70, 80 and 65, and my other constraint is age should be greater than 65. So I will be getting these 2 columns. So these 2 students with age 70 and 85. Look at the answer. So there are 2 students. So the answer is actually 2. There are 2 female students with age greater than 65, which means the student name B with age 70 and student name B with age 80. So yes, so overall these are the 2 questions which I have covered in today's class. So we started with steps involving query processing. Then I have taken you relational algebra. I have covered you all the same 5 basic operators, followed by I have solved 2 examples relevant to the topic, today's topic. Yes, thank you.